Hello. In this video, I'm going to demonstrate a highly educational circuit which can also be used to measure the slew rate of op-amps. And I'm going to measure the slew rate of the LM741 op-amp and the much faster OP37 op-amp. This circuit is taken directly from a video that W2AEW did about a variable sawtooth generator. This is it, the variable sawtooth generator. I'll put a link to the to Alan Wolke's video in the description of this video. This is an absolutely fantastic circuit. If you replace these two 1K resistors with potentiometers, then with variable resistors, then you can change the rising and falling edge of a triangle wave, of a sawtooth wave. And here's the circuit. Oh, and in this circuit, the op-amp is being used as a comparator, which is why we can measure its slew rate, because it's supposed to have ideally an infinitely fast transition from low to high, because it's being used to turn on and off a switch, which is this diode bridge. By the way, all of the diodes are 1N4148 diodes. These absolutely fantastic small signal diodes. Super cheap. If you don't have them, you have to get them. I got 100 of them for $1. This is like the best purchase ever. These are absolutely fantastic diodes. So here's the this is the output from the op-amp, which drives the diode bridge to switch the current sources. Basically, the way it works is it uses a constant current source and a current sink to charge and discharge a capacitor. This is a very special NP0 type ceramic capacitor in a glass case. So you can see here the square wave is not very square because we're using a 741 op-amp, which is kind of slow. And by just measuring the slope of the rising and falling edges, we can measure the slew rate of the op-amp. So let's do that. Oh, and one comment I want to make is that the slew rate limitation of the op-amp doesn't really affect the operation of the circuit. You can see that we get very sharp transitions between charging and discharging the capacitor. So actually, the 741 op-amp does just as good a job as this OP37 op-amp will do. So you don't need a fast op-amp or comparator for this circuit. As you can see, a very slow op-amp works just fine. We get a nice and sharp triangle wave or sawtooth wave. But anyway, we're here to measure the slew rate. So let's measure the slew rate. Adjust the horizontal position. And basically, I'm just going to use the vertical time cursors. We're going to do a time measurement, and we're going to measure the amount of time it takes for the voltage to change 8 volts, and that's because it's 4 divisions. It's a very convenient amount of change, and it's 2 volts per division, so that's 8 volts change, and you can see it takes 15.86 microseconds. So if we do the math, that's 8 volts per 15.86 microseconds, which is just over half a volt per microsecond, 0.504, and that's exactly what the datasheet says. And if we now trigger on the negative slope, adjust the horizontal position, bring up the cursors, adjust them, do all that. Oh yeah, look at that, it's pretty much the same, 15.9 versus 15.86, about half a volt. So for this op-amp, for the 741 op-amp, it takes about the same amount of time. The slew rate of the rising and falling edge are almost the same. They're pretty much exactly equivalent, exactly equal. But that's not going to be the case for this much faster op-amp, the OP37. So right now I'm going to pause the video. I'm going to change out the op-amp and the timing capacitor, and I'll come back. All right, I'm back. I changed out the timing capacitor so that for a smaller value, so that the frequency of oscillation would be higher. You can see we have the op37 op amp, and we want the frequency of oscillation to be higher simply because the rising and falling edges are now so much faster. It would be kind of difficult to focus in on them, but the higher the frequency, the easier it is. So here we go. It's that easy. We slightly adjust it, bring out the cursors. Oh wow, that one's already in the perfect spot. Right there. Let me just show you this. Nice. And you can see that's about 700 nanoseconds for 8 volts of change. So that's 8 divided by 0.7 microseconds, about 11.4 volts per microsecond. That's for the rising edge. But as we are about to see, the falling edge is significantly faster. All right, so it's about 531 nanoseconds for 8 volts of change. So 8 divided by 0.531, and we get, look at that, 15.1 volts per microsecond. So that's quite a big difference. That's, you know, a difference of about 3.6 volts per microsecond of between the rising and the falling edge slew rate. I don't know why that is. I could probably answer that question very quickly just by Googling it, but I haven't done that yet. So yeah, very interesting circuit. Obviously, the purpose of the circuit isn't to measure the slew rate of an op amp. The purpose is to generate a variable slope rising and falling edge sawtooth wave by replacing these two resistors with potentiometers. But I mean, this is a very educational circuit overall. It can also be used to generate an adjustable sine wave by just filtering the output triangle wave. Obviously, we would have to take the triangle wave and buffer it with another op amp first. But this since the op amp is being used as a comparator, this is a convenient place to test the slew rate of op amps. So yeah, that's pretty much it. It's a pretty cool circuit. It's a very cool circuit. It's absolutely fantastic. Huh, for some reason that's kind of non-linear. I would have expected it to be linear. That's actually interesting. How about we change that capacitor out for the other one, see what happens. Still kind of bad, wow. What the hell is happening there? I actually have no clue. I'll have to investigate that. For some reason, the square wave is fast, but the charging is highly nonlinear. It's supposed to be linear. With the 741 op amp, it was linear. So we're using a much better op amp, but the circuit performance is worse. Anyway, I hope you learned something. Have a good day.